In this last chapter, we take a look at the effects of radiation due to nuclear sources, but also discuss ionizing radiation in general and its effect on the human body. Now, really, this is a subject that could take up an entire course, and we're just going to, talk about it very, very superficially. Really, this is better left to a radiation health specialist for advice on radiation safety. But in any case, looking at what we're talking about, there is a great deal of fear about nuclear radiation because of its ability to ionize matter. And what are we talking about ionizing radiation? Well, first of all, radiation is the propagation of any type of energy. And in general, the term radiation in physics means something very different than what normally people think about radiation in public. In physics, again, propagating energy doesn't necessarily mean that it's going to be hazardous to our health. Light is radiation. Infrared light is radiation. These don't have the same effect that ionizing radiation does. So when we hear the term radiation, we're probably talking about this dangerous form of radiation that has the ability to remove electrons from atoms. And of course, this is what ionizing radiation is. Now, before radiation can be considered ionizing, each particle of radiation has to have more than 5 electron volts of energy per particle. And this is essentially what's needed to remove an electron from most of the elements that are found in biological tissue. So this is very, very important. I think oftentimes we've associated microwave radiation with cancer, and that's been highly controversial. But if we look at the photons in microwaves, it's not ionizing radiation. It doesn't have enough energy to remove electrons. Really, with microwave radiation and any type of non-ionizing radiation in the electromagnetic spectrum, the only damage that they can really do is due to thermal damage, due to heat, due to the absorption of a large amount of energy here. But ionizing radiation is very special in that it can remove an electron at almost any intensity. And that is why we have to be very cautious about it. Now, how does this do damage to our body? Well, organic matter or biological tissue is very, very susceptible to ionizing radiation because these are fairly fragile molecules. Protein molecules can be altered by ionizing radiation. If we get a very, very large amount of ionizing radiation, this will affect a lot of the molecules that we find in our central nervous system. And it can be dangerous in the short term because it can disrupt our central nervous system. It can disrupt other vital organs to our body. But that's very unusual that we receive that much radiation, that we damage enough of this biological tissue that it affects our lives and even becomes life endangering. It's the ionizing radiation that comes in contact with our DNA, which usually creates the greatest threat to us because that's where it has the highest probability of health effects. That if we're exposed to a large amount of ionizing radiation, this in fact can lead to cancer due to alterations to our DNA, and this cancer can be life-threatening. So again, when we're talking about damage due to ionizing radiation, we have to break it down into two different categories. One is a short term, where immediate damage from the ionizing radiation disrupts our biological systems. And then we have the long-term damage, which is done to our DNA, which can increase susceptibility for getting cancer at a later date. Now, again, ionizing radiation, if we're looking at the electromagnetic spectrum, we're only concerned really about three different categories here. Ultraviolet light, which we discussed much earlier in the course in terms of its danger for skin cancer. This is not nuclear. It is caused by some very hot source, such as our sun's corona, or from a discharge lamp. X-rays are also ionizing. They're more penetrating than ultraviolet, but as we discussed earlier, X-rays technically come from electrons in atoms and are not associated with the nucleus, not directly. When we have internal conversion, we can end up getting an X-ray. Gamma rays are really where, when we talk about nuclear radiation, we're talking about this part of the electromagnetic spectrum. And gamma rays have the highest energy per photon, but they're also the most penetrating, which means that it is the most difficult type of electromagnetic radiation to stop. If you remember, we talked about radiation first being discovered, alpha, beta, and gamma. Alpha was easily blocked, beta a little more difficult, but even our skin can block most beta radiation. But gamma radiation, we actually needed significant concrete or lead shielding in order to stop. Now, what does ionizing radiation do to our bodies? Well, the gamma rays, being electromagnetic radiation, can strip off an electron. But remember, we also have the alpha and beta particles, which if we ingest a radionuclide, that emission of the alpha and beta can do damage to our body, because the alpha particles and the beta particles are moving nearly at the speed of light. And when they come in contact with an electron, they are going to have more than enough energy to remove it. Remember, typically alpha and beta particles, we're talking about ranges of kiloelectron volts and megaelectron volts. So in terms of removing an electron, 5 electron volts, 10 electron volts, that's not a difficult task for these particles to do. In fact, they oftentimes will remove many electrons in sort of a cascade effect. Now, again, large amounts of radiation are very, very unusual. We are constantly bathed in radiation. And in terms of radiation and cancer risk, we increase the probability as we increase our exposure. But number one, our body can handle low-level radiation pretty effectively and repair the damage due to it. And number two, every particle of radiation has the possibility of creating a mutation that can lead to cancer. And even people with very high doses of radiation don't necessarily get cancer later in life. So it's really a game of probability. Just like anything associated with cancer, there's genetic susceptibility, which means that some people exposed to radiation become more susceptible to cancer because of their own, what mutations that may be contained in their DNA before they're exposed to the radiation. But again, it's really a game of probability. So what about our DNA being hit with radiation? Well, first of all, it does have an error correction mechanism in it. And of course, I'm not a biologist, so I don't know the complete details of this, but we are constantly being exposed to radiation. So through evolution, our DNA has developed a way of checking for errors. If you remember DNA, you have your different bases, and only one base can lock into a certain other base. So if we create some type of error through ionization, our body can repair this if it's detected in a timely fashion. At least that's the way I understand it. And again, we are constantly being exposed to radiation. The problem becomes when we get exposed to so much radiation that the number of errors becomes very, very great. Now, normally, For a cell, if an error occurs in the DNA, okay, the most probable thing that will happen if it's not repaired is the cell will either become dormant, okay, it'll just basically, there's a fail-safe mechanism that just shuts down any type of cell division, because we know uncontrolled cell division leads to cancer. Or number two, it undergoes cell death. It basically, commits, cellular suicide, and that removes the chance of getting cancer. It's a very rare case that a mutation occurs and this mutation is not addressed. Sometimes a single mutation can lead to cancer. Oftentimes it's multiple mutations that lead to cancer. Again, this connects with the earlier idea that some people have more susceptibility to cancer than others. So it's the intense short bursts of radiation that we really have to be mindful of. And cancer caused by a short burst of radiation is, again, a game of chance, but your chances of getting cancer increase dramatically once we go over recommended exposure amounts. So in terms of exposure, how do we measure how much exposure that we have? This is different from activity. Remember, activity was measured in curies, or it was measured in becquerels, in terms of how many decays a particular element undergoes within a certain time period. For instance, 1 curie is a huge amount of activity, 3.7 times 10 to the 10 particles per second. But your exposure depends on how close you are to the source, okay? How active the source is, all right? And also what type of radiation is being given off by the particular source. So, in terms of exposure, activity does play a role, but again, how close you are and how long you're next to this is really important. Now, damage to the human body is better quantified by the SI unit known as the sievert. There's also the CGS version of this, which is the rem. The sievert is equal to 1 gray. Gray is the amount of exposure that an object gets multiplied by something called a quality factor. So, for instance, gray would be, essentially, so many particles pass through your body per second. A sievert would be what type of radiation is going there, because some things such as alpha particles and beta particles, once they're inside your body, do much more damage than a gamma ray will do. So 1 sievert's equal to I got this backwards. Oh my gosh, look at that. Reverse that. 1 sievert is oh no, I did get that correct. 1 sievert's equal to 100 rems. So basically your rem is a much smaller quantity. I apologize for that. So what is this quality factor? Well, if we think about radiation, if we're exposed to an electron, we're exposed to a photon, these are typically 1-to-1 type events, meaning that one electron will typically only kick off another electron. Yes, there's a possibility for very energetic electrons kicking off multiple electrons or ionizing multiple atoms, but that's less probable than for other particles. Typically a gamma particle comes in, gamma ray comes in, it ionizes 1 atom, an electron comes in, it ionizes 1 atom. So we assign it a quality factor of 1 for radiation. However, protons, because they're 1,000 times more massive than an electron, when they come in, are less likely to be stopped by their first interaction. Additionally, when they interact, they give off so much energy to the electron that they release that that electron can go off and create additional interactions. Neutrons have quality factor between 5 and 20. It depends on the energy. Some thermal neutrons are less penetrating than fast neutrons. So the type of neutron and its energies really does make a difference there. And then finally, any type of alpha particle or nuclei have quality factors which are assigned around 20. And, alpha particles, as we talked about earlier, alpha particles and electrons don't penetrate very deeply into the body because of the nature of the particles. Nuclei penetrate even less, but with nuclei, when we're exposed in space, astronauts, for instance, are exposed sometimes by these nuclei, traveling at very, very high speeds. And we don't quite understand, the danger of these nuclei yet, but again, we give them a quality factor of 20. So how much radiation do you typically get and where do you get it from? Well, the typical dose of radiation depends on where you live, okay? Depends on how much uranium and thorium is in the soil. This leads to the release of radon. It depends on, how many, medical x-rays that you get, type of building you're in, even what you drink. There's something called a banana equivalent dose because bananas have iodine in them, and a very, very small amount of radioactive iodine is delivered to your body. No, potassium from banana. But don't stop eating bananas. It's not really significant. And of course, cosmic radiation becomes greater as you go to higher altitudes. But again, 2.4 millisieverts per year is the typical dose. Higher altitudes, higher doses, certain geological areas, you're going to get more radiation exposure from that. Here's another breakdown. In this breakdown, for this particular area, is 50% of your radiation came from radon. In this breakdown, it was 55%. But again, you can see radiation comes from so many different places that you're not going to get rid of all the radiation in your life, and nor should you be so concerned about it. Your body is very well equipped to handle this. And just because somebody gets cancer doesn't mean that it came from radiation. There's just so many different factors out there that natural radiation really isn't a huge culprit. Where it becomes problematic is when we produce structures which trap radon. This can really increase the amount of your exposure, because when radon gets into the body, it has a very short half-life of a few days, and it can decay from a gas. Radon is an inert gas into something that's solid. Now, if we go back to the uranium decay chain, we can see that radon 222 is right here. So if you inhale radon, okay, radon 222, it will decay into polonium, which is now a solid, which means that if it did that while it was in your lung, it's now trapped in your lung as polonium. And that will decay through a series of other decays, alpha and beta decay, which can expose your lung cells to elevated amounts of radiation. Radon from thorium produces radon 220. And again, this decays to radioactive polonium, a different isotope, but again, it's still radioactive. So we have to be careful that our homes aren't leaking radon from the foundation into the rest of the house. Typically, we don't have to worry about radon outside. Radon just goes up to the atmosphere and it's diluted. If we have a house or a building that acts like a cap, where the radon comes in and then it gets trapped, then this becomes a problem. And it's a problem where thorium and uranium is more common in the soil. And we can see out in parts of the Midwest, the northern part of the Midwest, there's a bit of uranium. In the parts of the northern Rockies, there's elevated doses, and elevated doses in the Appalachian Mountains. Okay, so even when we look at New Jersey, we do see an elevated risk, especially in the highlands and the Piedmont areas, where there tends to be, believe it or not, more uranium and thorium in the soil than you have in the coastal places. So when purchasing a home, one of the things that you're supposed to do is get a radon test. And they put a little canister in your home and try to see if radon is accumulating in the home. And usually, if the house is really well sealed, meaning that it's insulated and thermally tight, you're going to increase the amount of, or concentrate the amount of radon in the home if there's a crack in the foundation. So what is a maximum amount for the body? I mean, according to regulations, what are you allowed to get per year? Okay, so let's go back and see what the natural amount of radiation was that we typically get. So 0.0024 sieverts, or 2.4 millisieverts, was the maximum amount. So when we look at this, it's actually 50 millisieverts, okay, or 5 rem. Usually the US government uses rem as opposed to sieverts, which is the annual limit for occupational exposure for anybody working. So, generally they're keeping it, a bit above what the natural amount would be. But through studies, they've determined that this dose of radiation is more than fine for your body to handle. Now, in the cases of emergency, there are different levels which they allow. Here, and I'm not going to read through the entire amount, but it says damage zone and fallout areas around a nuclear detonation site. I guess, they're talking about a dirty bomb, excluding dangerous fallout zones and elevated radiation areas. 100 millisieverts is the maximum amount. For more immediate dangers, it bumps up to 25 rem, or 250 millisieverts. And then for the most extreme examples, where the good of the many outweigh the good of the individual in this case, they allow for even larger exposures. But as we'll see, even at a quarter of a sievert, you're not increasing your chances of getting cancer. Well, you are increasing them, but not dramatically. So again, in terms of the exposure, again, they do it per year. Your entire body shouldn't be exposed to more than 5,000 millirem. And again, if you're going back, this is 5 rem. So that is our limit there. any individual organ shouldn't get more than 50,000 millirems per year. How does that, I have to really look into that to see how that works out. Your skin, because your skin can block alpha and beta, shouldn't be exposed to more than 50,000 millirems per year. But for pregnant women, exposure should be limited much more. Okay. 500 millirem, represents about twice the natural amount of radiation that we receive. And members of the public should not be inadvertently exposed to more than 100 millirem per year. This is on top of what you get naturally from the 250 millirems per year. Okay, so what happens when we are exposed to very, very large amounts of radiation? We don't just worry about the changes that have been made to the DNA. We can actually damage biological tissue, even up to and including burns. So acute radiation damage does lead to immediate health problems rather than just worrying about cancer down the road. So below a quarter of a sievert, which was the maximum for emergencies, there's usually no immediate detectable effects, but your cancer risks do increase. The acute effects shouldn't say, we call them acute effects. The immediate effects would start above a quarter of a sievert up to a sievert. Here, you wouldn't necessarily notice it. There might be a change in your blood work. Sometimes people who are sensitive to these changes can experience nausea, but for the most part, somebody receiving under a sievert of dose would be completely unaware of it unless they had a dosimeter on them or they're informed of it. Above a sievert, this is where things get really bad. In 10% of the cases, it's fatal after 30 days. So 9 out of 10 people do survive this, but nausea, diarrhea, decreased blood count. Here, when we're getting into this range, we're really worried about infection because radiation kills the most rapidly dividing cells. Okay, that's why it's used, against cancer, but it also kills our white blood cells, which help us, fight off infections. Typically, somebody exposed to this won't really start feeling this. This is why it's insidious. Until about 3 or 6 hours after the initial exposure, they're going to start feeling sick. 2 to 3 sieverts. Here, more than a third of the people exposed will probably die without, extraordinary intervention. Here, symptoms begin as soon as 1 hour after. And again, they're similar to what we saw before, in addition to people at these levels usually become permanently sterile. From 4 to 6 sieverts, most people succumb after about 30 days. Just more symptoms than we had for lower doses, in addition to internal bleeding. Anything above 6 sieverts is usually fatal, although people have survived. Okay, usually though people succumb after 2 weeks, and the humane thing to do is to heavily sedate people who are exposed at these levels. Survival is only possible with a bone marrow transplant because essentially your source of new blood cells has been destroyed, and somebody who's exposed will begin to feel the damage about 15 to 30 minutes after being irradiated, and this will probably result in internal bleeding. And they don't list it here, but probably some central nervous system problems. Above 10 sieverts, the cell death is too massive, and especially in the nervous system, you'll get the nervous system, shutting down, or your cardiovascular system shutting down as a result of these high exposures. So again, people can linger for a while. There's actually a latent period, with a lot of these people are exposed, where they get sick immediately. Then they have a few days where things seem a lot better. And then things continue to go downhill because the progenitor cells that produce blood, produce a lot of the other things, they can no longer produce new cells. And as the old cells die, nothing replaces them, and the body just deteriorates. And again, usually this is fatal after about 10 days. 50 to 80 sieverts, damage to the central nervous system is so severe that people become disoriented, go into a coma, and then normally just die. And 80 sieverts and above is thought to be instantly fatal. So people die quickly after such a high exposure. But again, I'm sorry to go over this horror show again. It's very, very rare that anybody would be exposed to such high levels of radiation. You have to be in contact with a very unusual event, such as a Chernobyl, such as being exposed to, there have been people who've stolen radioactive samples, much to their dismay later on, such as cobalt sources from hospitals, or radiothermo isotope generators in the Soviet Union were oftentimes pilfered for pieces. These would be used for remote stations, and people would open them up and expose themselves to high doses. But again, very, very unusual that you'd ever be exposed to anything close to this. So again, with radiation damage, we have the early effects, the somatic effects, which as we saw, can immediately cause changes to the body, and lead to what we call radiation sickness. And then, of course, we have the later effects, which are changes to the DNA, which can increase our risk of getting cancer. The irony of nuclear radiation is that although it is very dangerous, as we saw, it can lead to some very severe effects to the body, because it tends to attack or tends to affect rapidly dividing cells. It's very effective against cancer. And really, if you think about somebody who suffers from radiation sickness, their hair will oftentimes fall out. Their skin will appear to be, gray, unhealthy. The gastrointestinal system becomes disrupted. These are all, parts of the body which have rapidly dividing cells. Hair cells are rapidly dividing cells. Skin cells are rapidly dividing cells. The lining on the gastrointestinal system has rapidly dividing cells. So these are the parts of the body which are most affected by the radiation. Cancer cells are even more susceptible to it. So the general technique is, if we can concentrate, we call the stereotactic radiation, if we can concentrate the radiation such that it is most intense only at the tumor site, we can very effectively disrupt the tumor, causing it to shrink, or maybe even cure the tumor. So radiation therapy is oftentimes used as a way of shrinking a tumor before it's removed, reducing a tumor where the goal isn't necessarily cure, because in some cases a cure is not possible. But if we can shrink the tumor, we can improve quality of life, or we can shrink the tumor enough that the body can effectively attack it on its own. Stereotactic radiation is an art where you're really trying to map out the tumor itself and getting different intersecting beams of radiation to converge at that point. So the tumor will get a lot of radiation, maybe hundreds of times more radiation than the surrounding cells, and this can preserve the healthy cells. So, again, radiation is a very dangerous thing for our bodies, but again, our bodies can handle most levels of radiation that we'll ever be exposed to. Also, it can be a very effective tool in attacking cancer, which again is that irony that it can cause cancer, but if used properly, it can also be a weapon against cancer.